So anyway, my name is Munir Kaderbhai, and today I'll be talking about load attributes and generator set sizing. And so I was kind of debating which route to take. Many of you are familiar with GenSize and have used it before. Some of you haven't. So I wasn't sure whether to focus more on the tool itself or just on the general principles to follow when sizing a project. So I've tried to mix in a little bit of both. And so I think what I'll be doing, if you're around later on next week, if you want to, I can schedule a session just for the tool itself. So I think Anne was interested in that. So with that, what's the #1 rule when it comes to sizing gensets? Don't trust. Don't trust your sizing tool. Yet, okay, yet. So some learning objectives. So there are two types of loads, I guess, if you were to lump them together, that get people into trouble when sizing gensets are any type of motor loads. So when I say motor, it could include like any AC with a compressor or things like that. And the other one is, I guess, if you put in a bucket, it would be nonlinear loads. So I'm going to focus the majority of this time talking about those two loads. So we'll talk about the electrical characteristics of motors, induction motors, special requirements for sizing, and then we'll kind of transition and talk about transient performance of generator sets, and that will be kind of a continuation of some of the things that Julian talked about this morning. And then I'll finish with nonlinear loads, talk about special situations with UPSs, that's uninterruptible power supplies, and variable frequency drives, and general practices that you can apply to make sure you have your genset sized correctly. So with that, so first thing when you need is to have figured out before you size a project is you need to have paid attention to what Antonina talked about. You need to figure out, you look at your overall load profile and figure out what duty rating you want to apply for those. Then the next thing is obviously common sense things like frequency, voltage, what fuel, again, what's your ambient conditions, do you need to apply some D rates? And then you might have special voltage and frequency dip requirements, either governed by code. For example, if you have fire pumps in North America, then you have to maintain a 15% voltage dip limit. Otherwise, you just might have equipment which are sensitive to deviations in voltage and frequency dip. You might have to have mandatory steps. So you need to have figured out, okay, how many steps can I apply to the project? Am I legally required to? In the US, if you have a mix of emergency standby, optional standby, legally required and optional, you have to put them in different transfer switches. And then it always helps to have a sizing software like Power Suite. So with that, I'll jump into motor load. So let's see if people paid attention to Julian. So I'll give you a hint. Motor load is a lagging power factor load. So what power? What types of power does it require? And yeah, just real power and reactive power, and is going to be a lagging power factor. So motors can be tricky because they're no problem in steady state, but they take much more to start than to run. And different types of motors can have different starting requirements, so you have to be careful when you're analyzing those things when sizing a genset, because the starting requirements can either drive the size of the genset bigger or smaller, and it can make a huge difference. And then also, if you improperly size a genset, you could have huge voltage dips that might impact other loads connected to the system, forcing them to disconnect. You might not even be able to start the motor itself. So here's a brief, again, recap of what Julian talked about. You have a motor which is a lagging power factor load. It demands kVAR, or reactive power. So this is also sometimes called imaginary power. You need it to set up the magnetic fields. And then this is the kilowatt that's demanded by the actual load. kVAR comes from the alternator and is controlled by your excitation controls. And your engine provides the kilowatt, and that's controlled by a governor by varying the amount of fuel that you're sending to the engine. So the kilowatt's the engine, kVAR, and then this is the kVA, which is the apparent power. And as Julian said, the ratio of the kilowatt to kVA is the power factor. So let's talk about the three-phase electrical characteristics of an typical induction motor. So let's assume that this motor is starting directly across the line. You're not utilizing any soft starters or reduced voltage starters. So the first thing I want to point out is this green curve here, which is basically the inrush current. As you can see, the starting current is 600% of full load current. So basically, what does that mean? That means that the kVA is also much higher, right? So that's what we focus on when it comes to motor starting, is make sure that the motor has sufficient starting kVA to provide that inrush current. Then as the motor picks up speed, it'll kind of reach to the 100% full load amps. Now this is a good rule of thumb to use if you don't know details about a motor for typical NEMA design type motors, but you have to be careful about high efficiency motors. Although they save you energy in the long run, the starting requirements of those could be up to 10 to 12 times running. And the same thing applies for single phase. So you just have to keep those two things in mind. The other thing I'll talk about here is the relationship between kilowatt and kVAR. So this purple curve is the power factor curve. So as you can see in the beginning, when the motor first starts, the power factor is very low. So what does that mean in terms of kVAR and kilowatt? High kVAR, low kilowatt, but that can drive the overall kVA to be quite high, right? As the motor builds up speed, the power factor kind of improves and stabilizes to about 0.8, and at that point, kilowatt is high, and kVAR is not that much. So that's why, again, I'll repeat, when you're sizing for motor starting, make sure your alternator is sized enough to provide that high starting kVA in the beginning. The third thing I want to talk about on this slide is the relationship between the torque developed by the motor and the voltage at the motor terminals. So whenever you apply a motor to a genset, there's always going to be a momentary drop in voltage and frequency, or voltage and frequency dip. And the level or amount of dip depends, of course, on the relative size of your load to your genset. But when it comes to motors, can somebody tell me why it's important to watch out for the voltage dip? Exactly. So the first thing, like Julian said, is you'll always have that instantaneous voltage dip, which occurs right away before the AVR has had a chance to respond. So if you have magnetically held relays in the starters or things like that, if you exceed, let's say, 35%, then you will not be able to get the motor to start. There's also another second important reason. The torque, right? So the torque developed by the motor is proportional to the square of the voltage. So let's say if I'm 100% voltage at the motor terminals, I have 100% torque. If my voltage drops 10%, so now I'm at 0.9 per unit. So you square that, torque is down to 0.81. If voltage drops by 20%, my torque drops to 64%. So, the higher the drop in voltage, the less torque the motor develops, and it might not be able to start the load. So I'll just point that out with these two curves. So this red curve here is the motor torque developed at full voltage. Let's say starting direct on the utility, so no issues there. And this blue line is the torque requirements of the load. As long as there's a nice net difference between the two, you're good. You have a smooth acceleration. The motor will build up speed very fast, and you'll be fine. But now let's say you're in a genset and the voltage drops to about by 10%. So now this red curve, dashed red curve here is a reduced torque curve of the motor. So as you can see here, you're kind of just on the boundary between what the load is requiring and what the motor can provide, so you could stall, right? Or if you don't stall, it would drag out the acceleration time of the motor, and you'll be stuck in these conditions where you're drawing more current, and you could trip a circuit breaker because of overheating. So that's why it's important. So for some fundamental criteria for motor sizing is, one, make sure that you can provide that locked rotor kVA and minimize the instantaneous voltage dip so you can start the motor. Second is make sure that the motor can build up sufficient torque to drive the load. And you can do that by making sure that your alternator excitation system has enough strength to build the voltage up to at least 90% of rated voltage. And I'll explain that a little bit. So now I thought I'd talk about this a little bit. And this is our specification language for motor starting. And so we always say that motor starting capability shall be a minimum of X kVA, and you should be able to recover to at least 90% of rated no load voltage after that load is applied at the low power factor. So this is kind of consistent with NEMA MG1 standards. So the idea behind is that if you recover to 90% voltage, and this is now sustained voltage, so you've dropped the instantaneous voltage dip, and after that, you know what the voltage recovers to as the motor starts to accelerate. So as long as we can go up to this number, we'll have 81% torque developed by motor, so it's likely that it's going to be able to start the load, so we should not have any problem. In addition to that, we also say, we ask them to specify a voltage dip. And this, again, will make sure that we don't drop below the typical 35% threshold before it starts affecting the starters and things like that. But what I wanted to point out here is that not everybody, our definition of motor starting capability, or the number that's published in our alternator data sheets, the CPG, might not necessarily mean the same thing as what maybe Generac, for example, or Kohler might publish. So it often causes confusion. So I thought I'd maybe see if I can clarify a little bit. So first of all, there's the instantaneous voltage dip, which is the first few cycles. And that's a function of the alternator reactance and the requirements of the load. And so I think what I don't know, maybe you can correct me, but some competitors, they base the motor starting capability by saying that, okay, at this much kVA, the instantaneous voltage dip is going to be 30%, and so that's the motor starting capability. Whereas what we do is that we see whether the alternator can recover to 90% voltage. And I'll clarify this a little bit. But so this is more of a function of the exciter type and size. And again, it ensures that the motor can develop sufficient torque. Some competitors say that we only focus on this. We say that competitors always focus on this. But in reality, you should take both things into consideration, right? So when you size gensets in gen size, it's actually looking at both of the things. So for example, just to clarify like how some other competitor might define the motor starting kVA, they'll say, okay, let's assume that the motor can tolerate 30% voltage dip. So at 11,000 volts, the motor starting kVA is about 3,800. Because if you exceed that, you're going to have an instantaneous voltage dip higher than 30, and the motor won't start. I think what our numbers are based on this chart here. This is the alternator external characteristic curve or overload curve. And the way that it's been explained to me is that basically at the low power factor of 0.3, You ramp up the kVA until your excitation gets saturated, and then it can't support the voltage anymore, and you start to drop. And the point where it reaches 90% is the motor starting kVA, but they do some correction back to this 1 per unit. I still haven't figured out how to explain that. But basically, essentially, that our motor starting kVA is then 5,000. So ours is based on this curve, and most others are based on the locked rotor kVA curves. But one thing to watch out for is that for a given alternator, we might say that our motor starting kVA is this much. But if you were to look up the instantaneous locked rotor curve for the alternator, for the same for this much kVA, you'd have 35% voltage dip. So although we can recover to 90% voltage here, sustained voltage, the instantaneous voltage dip will exceed 35% and 1,500. So this, if the motor was the only load, having that extra kVA, so you see, I guess it can be misleading sometimes. All right, so although I talked about the impact of reduced voltage and the motor torque, in some cases, because of the large motor starting kVA requirements driving up the size of the alternator, it's beneficial to have a controlled reduction of voltage at the motor terminals. And so we have all sorts of ways to do this, reduce voltage starters. And I won't go into the details of this. If you're interested, you just got copies of the TO30. You can go to the Appendix A, and it explains all these different methods. But the key advantage is that they significantly help to reduce the inrush current. So that way you don't have to oversize the alternator too much. So for example, at full load, directly across the line, you're 600% starting current of full load amps. As you can see, once you go with auto transformers, you can reduce that quite a bit. The only caveat with this is that if you have applications like those high inertia applications which require a lot of torque to start, like rock crushers and things like that, you should be careful when to make sure that if you do use reduced voltage starters, you can develop sufficient torque to start those loads, because you might get into some trouble. The other thing too is, for example, if you use solid state starters or soft starters, they typically have a power electronic stage or some rectifiers which cause distortion. So although you might reduce the starting kVA because of the nonlinear harmonics, you might have to oversize again. So it's all a trade-off. So yeah, again, watch out for this, especially if you have high starting torque requirements. The other common thing or misapplication of reduced voltage starters is this. So whenever you use a reduced voltage starter, you always have a transition from starting mode to running mode. And when you transition, you could have a second inrush current. So in this case, let's say you program it to make sure that you don't exceed 400% full load amps. So you build up to 80% rated torque. And then once you transition into running, you'll have, again, the spike in the inrush current, but you're still not exceeding this 400% limit that you set. But if you transition too early, then you jump up to here, then you haven't really done much to help your situation. So that's something to watch out for. Okay, so some motor starting rules of thumb. We can generally start motors that we can also run, but that's provided that you're forced to meet a decent voltage dip or an acceptable voltage dip. So oftentimes when we get projects, people go into the project parameters and set a voltage dip limit of 10%. When it comes to motor starting, forcing a 10% dip limit for those kind of applications can mean that we have to significantly oversize the genset. And in some cases, for example, you might have the engine running too lightly loaded once the loads come back to steady state. And that can lead to all sorts of problems. As you know, for diesel engines, you won't run hot enough at loading less than 30%. So then you have wet stacking, and then you have carbon buildup in the exhaust manifold, and that means more maintenance, more cost for a customer. And so that's important. And also, you're unnecessarily buying an extra large genset, right? Of course, in North America, we have the 15% voltage dip requirement for fire pumps. So that's just, if you have a fire pump there, you have to meet that requirement. So that's something to keep in mind. So let's assume that you didn't have any way or calculator to size a genset for motor starting application. If you were to take a guess, if you assumed about 2 kilowatt per horsepower for direct across the line starting, then you'd probably be okay, but that's still very conservative. We tried to optimize more towards 1 kilowatt per horsepower, and there's a lot of ways you can help optimize the sizing. The first and most important is to try and apply the loads in multiple steps. So by doing that, you're reducing the surge requirements demanded by the engine and alternator at the same time, and therefore also reducing the voltage and frequency dip. So you can become much more optimized. And there's tons of ways to do it. You can use multiple automatic transfer switches. So for example, if you're in the US and you have a mix of emergency, legally required, and optional standby, you're going to have 3 transfer switches anyway, so you can use those to step the load. Otherwise, you can use programmable logic controllers, PLCs, or some loads have smart controllers within them, so they can kind of sequence themselves. The other key thing to keep in mind is that, so after you've started all your emergency and loads that you need to start right away, then try and start all your large motors as soon as possible. Because by doing that, you're effectively reducing the cumulative power requirements. For example, let's say if I had a huge motor, which I decide to start last. So now I have started all my other loads. And so I'm up to a certain kVA kilowatt output. And then I start the motor right at the end. So I have to add that huge starting kVA on top of the power that I'm already providing the other loads. So that can result in oversizing. And now I'll show you a nice illustration which shows that. The other thing is use alternative starting methods for motors. Bring down the starting requirements if you can. And the third thing is analyze your cyclic loads. So if you go into some types of loads in your facility, like HVACs and things like that, those are cyclic loads, which means that they'll start up, run for a little bit, then stop, and then start up again. So in GenSize, we actually have a checkbox which says cycle load on off. So what you can do is check that box. So that means that what GenSize does is it assumes that all the other load running, the non-cyclic loads, it factors in the kilowatt, and then it starts the last cyclic loads at the end. And so it makes sure that you have sufficient surge power to start that with all the other loads running. And at the same time, that's why it also has the peak voltage dip. So it also calculates the peak voltage dip to make sure that when those cyclic loads come on, with all the other loads running, you do not exceed that. But my caution with that is that I've seen many people will have like a few, some motors, and they select cycle on-off for every single AC or motor, which is going to be cycling on and off. But this will result in a very conservative sizing, and you'll oversize too much, and you'll end up running too lightly. So what we generally recommend is that analyze your load, right? Because what GenSize does is that it assumes the worst case scenario and considers all those cyclic loads turning on and off at the same time. So, in reality, it's highly unlikely that unless they're programmed to do it, you might have loads coming on and off at the different times. So generally, we say, pick 2 or 3 of the biggest cyclic loads, check them with cycle on off, and leave the rest unchecked. So that way you'll probably be safe, but not too oversized, right? So again, use multiple transfer switches, put on your essential loads first, then your equipment loads, and this would be non-essential loads. So here's what I was talking about if you try and start all your large motor loads first. So this would be the starting kVA and then starting kilowatt. So ideally, in this case, by applying steps and using reduced motor starting for soft starter here, soft starter here, you're kind of gradually building up, and you're still within this initial worst case situation. But now imagine if you had this started at the end. This curve would be way up. So that's why you have to be careful about how you sequence your loads onto the genset. So some recommendations. We recommend that you try and split up your load to at least 4 steps, if possible, using multiple transfer switches. And then other key thing is to make sure that you allow sufficient time, recovery time between each step. Because generally, depending on the percent step load, it could take 2 to 3 seconds for the voltage and frequency to recover to nominal. And then start larger loads first. We talked about that, and used alternative starting methods. And some spec language we suggest to customers is, when you specify a maximum allowed voltage dip here, it should be with respect to the maximum step load, not the generator set power. I don't know if it's done differently for you folks there. So when you specify the maximum step voltage dip, is it based on the genset rating, or I guess it depends. If, let's say, we're not talking about ISO. Right. Yep. The other thing is that if you have sensitive loads, for example, like electronics, which cannot tolerate voltage dips as low as 10%, then what we recommend is that put them on those sensitive loads on the UPS, and then you can put the UPS on the genset. So that way, you don't end up, if you have some computers or stuff or equipment, which can, when you reach towards 10%, they don't like it too much, then you can put those loads on the UPS. Then again, going back, this is just the original language for our motor starting kVA. And again, make sure that you can recover to 90% rated. So probably we need to sit down and discuss this again. So now let's talk about generator transient response to load steps. So why do we have voltage and frequency dip? I guess the answer is kind of like that. This is how I like to think about it. It's an imbalance. It's a momentary imbalance of energy, right? Your demand is exceeding your supply. So let's take a look at this curve right here. And this is an exaggerated curve. Our performance of our machines is a little better than this. But let's assume that you're starting a low power factor load like a big motor. How is the generator going to respond to it in the first few cycles? So this red curve represents the voltage, and this black curve represents the frequency. So the moment you start the load, you're going to have an instantaneous drop in the voltage and frequency. So I'll start with this red curve first. So initially, you'll have the instantaneous voltage dip. And what does that depend on? What's that? Yes, the load, of course. And anything else about the alternator? Right. Subtransient, the reactance. So basically, you'll have the initial voltage dip, and then the AVR, which is the brains of the alternator, decides to wake up over here and starts pumping up excitation and helps the voltage recover. And then it overshoots a little bit, and the excitation is kind of goes up and down until it reaches steady state. So what can we do to limit this? We already talked about why this instantaneous dip is bad. But what can we do to minimize that? So it's a function. It depends on the subtransient reactance. So what? So right. Or we could somehow reduce the subtransient reactance by oversizing the alternator, right? So usually a subtransient reactance of 12% is good for motor starting. But by oversizing the alternator relative to the load, we can minimize this voltage dip if it becomes an issue. So again, this black curve is the frequency dip. And so the moment you apply the load, the load demanding energy, real kilowatts from the engine. So the fuel is being consumed more than the governor is supplying. So then the governor kicks in and starts pushing more fuel to the engine and helps the speed recover and therefore frequency.
Can I ask you a tricky question?
Yes.
Where are my 90% in there?
You're 90%?
Yeah.
So let me show you another curve, okay? Okay, let's see if we can figure out from this one a little better. So in this example, this was assuming a low power factor start. That means that the engine is not too heavily loaded during the start, right? The alternator is doing most of the work in providing the VAR, so because the kilowatt is small. But let's say now we have NFPA testing, 110 testing, which is done at 0.8 power factor, right? So now it's a completely different story, right? The engine is doing more work than the alternator because you're providing more kilowatt now. So how is the transient response going to be a little different? So hopefully this can result in some more discussion. But the key thing is for your genset is the last thing you want to have happen is for the prime mover to slow down, right? Because prime mover slows down, your voltage will drop. So recovering frequency takes precedence over recovering voltage. So let's take these two curves. It's for like a 15-liter engine, 500 DFEK model. So this is the frequency, and this is the voltage dip, and this is the frequency dip, and it's 100% step load. So you apply the step load, you have an instantaneous drop in voltage, and the voltage starts to recover right here. It's a slight dip, bump, but as you can see, the frequency is still dropping. So that basically means that the engine needs some help to recover speed. So what the controller does is that it starts to roll off the voltage a little bit to unload the engine because, again, the load is proportional to voltage. By reducing the voltage on the engine for a little bit, it'll help the engine speed recover, and then the voltage will also recover eventually. So the moral of the story is that torque matching or the under frequency roll-off function of the controller can sometimes skew the voltage dip. So just looking, if you want to estimate the voltage dip, just looking at the lock rotor kVA curve is not enough because you might get an even bigger voltage dip because the controller forces it even lower to help unload the engine. And so in the PCC controllers, we have this roll-off table, and it follows the curve like this. So for example, if you have 60 hertz, no problem. Up to 59 hertz, no problem. But now if you start slowing down, it's going to reduce the set point of the voltage to less than rated. So that's something important to keep in mind. So what I want to share with you, I thought this would be some good discussion, is some results of some experiments that were done to try and see, the impact of different configurations of gensets, like alternator voltage, power factor of testing, and what was the effect of that on the voltage and frequency dip. So some of the X variables that they did when they were testing the 50-liter sets was, what's the impact of voltage, the alternator frame, the power factor, They even checked controls, but found out that they were quite transparent in the response and the power. So I have some interesting slides here. So they did the experiments at 60 hertz at this different voltages with this 3 different frames and 2 power factors, and similarly at 50 hertz. And so these were all the combinations that they did. Yeah, so for example, 1500 0.8 power factor with the P7C at 480, and they did some runs with all these. So some interesting results, I guess. For example, this yellow curve is at 380 volts, and this purple is at 480 volts, and up to here, this is load steps going from 0 to 100. 0 to 75, 0 to 25, and this is basically load rejection. So now you're going from 100 to 0. So as you can see, the voltage difference doesn't seem to have much impact on this part of the curve, on the voltage dip. But it has a significant impact on the overshoot. It's quite different, right? Why do you think?
Is it actually nominally the whole overshoot is the same? It's just when you're doing a percent,
yeah. So this is so in this case, the purple 100% voltage would be 480, and so the excursion would be a percentage of 480 versus in the yellow line, this excursion would be a percentage of this voltage. So it's probably maybe because at 380 volts. For the same rating, you have more current. So when you go from load to no load, suddenly you have the initial, I guess if you draw the simplified model of a machine. Right, and so, right. Recovery time, I guess no impact here, no observable pattern here. So the interesting thing though is that as far as the frequency or the engine, doesn't seem to matter at all. The reactance is almost the same. So I guess the conclusion will be that the voltage is more, especially with the drop load, voltage excursion is a more critical factor there. Then this was the voltage dips with the different frames, the P80, then the P7 with the G and C. And as you can see, the difference in the dips, especially if going to 100%, is quite different. And also with the load rejection, the overshoot is quite different. And before I maybe offer an explanation, frequency is almost the same. So we know that it's not affecting the engine. It's all purely because of the alternator. So why do you think this is different? We know that it's not because of the engine. The engine maintained the same speed. So we know that it's not an impact of the, torque roll-off function or something. But what could be different between this or, because it's at the same voltage? Yeah, that's what I would think, right?
What?
The reactance of the equipment. Can anybody give a pattern from this? No. The recovery time doesn't seem to follow any observable pattern for voltage. This is the most important one, actually, especially here, because this is the difference between the performance at 0.8 and 1.0 power factor, right? So we mentioned before NFPA 110. You have to do testing at 0.8. So they bring the machines here. They test them at 0.8 power factor. Then the customer takes them to the installation site, and they want to test it there. And it's much more expensive to get inductive load banks, so they get resistive load banks at 1.0 power factor. And all of a sudden, they're getting much more worse voltage dip than what they measured at the factory. And they say, what's up? So as you can see, for the same percent load step in terms of kilowatt, at 0.8 is like 35, but at 1.0 is almost 10% more at 1.0 power factor. And then also it has a big impact on the frequency. I mean on the, when you do a step drop. Percentage of the kilowatt. They always go by the standby rating of the gensets here.
So when you say not 50%, it's not 50% of the kilowatt.
Yeah, so it's the same kilowatt load on the genset at this point, just at different power factor. The kVA is different. So I guess my reasoning might be that when you have a 0.8 power factor, even though the engine load is the same, but because of the higher kVA with 0.8, you have more kVAR, so you have more current. So the initial instantaneous voltage dip will be higher. So that helps unload the engine. And so therefore, because of the roll-off and whatnot, the final voltage dip won't be as bad as with 1.0. Because now you have, with 1 power factor, you don't have the extra. The instantaneous voltage dip might be lower, but that means that the engine is initially heavier loaded. So therefore, the recovery will force, because of the roll-off function, it'll force the voltage down more. I don't know, what do you think of that theory? It's a huge difference, right? 10% dip. And so same thing with the frequency, 16 and 10. So right now there's actually an effort to make sure that we are collecting data at the factory at both power factors, at 1.0 and 0.8, so that in those cases when the customers kind of challenge us, we can give them a better explanation of what's going on in terms of the overall performance. Okay, so before I jump gears and talk about nonlinear loads, are there any questions so far? I'll just focus on some key aspects first. So when it comes to nonlinear loads, from what I've learned so far, what we need to worry about more is the impact on the customer's loads connected to the genset. So there'll be voltage distortion, and in most cases, with the alternator oversizing and things like that, the alternator is probably going to be fine. But we have to see that is the equipment on the genset, on the customer's end, going to be able to tolerate that. So basically, we need to size the genset appropriately to make sure that we control the level of voltage distortion. So who advises on the maximum level? I guess this really depends on the application engineer and depends on the type of equipment. The limits are slightly higher than when you're running on the utility. But these were some guidelines that we got from CGT folks. So UPSs can typically tolerate 10%, inverter drives 15%, and any soft starter or diode-based rectifiers can be up to 20%. And then, obviously, the type of equipment that you have connected to the genset will also govern that, right? If you have, dirty 6-pulse rectifier equipment, they can induce harmonic currents up to 30%. That means you get more voltage distortion. But the higher you go in cleaner pulse technology, you can reduce the current distortion. So that's also a key thing. So let me jump into this and discuss some common characteristics of a nonlinear load or a rectifier. So one thing that you'll know is what's the generator seeing, right? Is the part that the generator sees which we care about. And so that's commonly referred to as the front-end electronics. And for example, in this case, this is the most basic 6-pulse diode rectifier. And then you'd have some sort of, so this basically takes the AC waveform and converts it to a DC. And they have a capacitor here, which is called a bulk capacitor, which maintains the DC voltage. And then you could have another power electronic stage here, which could be another inverter. So, you know, you can see these in soft starters, UPSs, variable frequency drives. Here's another example. So this is the front end power electronics. There's a double conversion IGBT rectifier. You know, there's pulse width modulation, very clean when it comes to harmonics, very reliable. So why do we care about the type of rectifier? Well, for one thing, pulling a distorted current through an impedance will cause voltage distortion, right? And voltage distortion causes a whole bunch of bad things. So I'll just focus on this slide here. So for example, you could have a 6-pulse rectifier, 12-pulse, or an IGBT supply. This is the typical waveform, what a waveform for the current would look like. This is a 6-pulse, and it's called 6-pulse because if you see it's got 6 pulses. And this is a 12-pulse, which looks more cleaner. And the higher the number of pulses, the closer you get back to a clean sinusoidal waveform. But the reason why you have to be very concerned about this when you're on genset, because genset is a high impedance power source. So the impact of this same level of current distortion can be quite different between a utility transformer and on the genset. So for example, this column represents the generator set, and this is like a utility transformer. This is the short circuit ratio, which is kind of like a measure of the impedance of the system. As you can see, the voltage distortion on the genset is much, much higher than on the utility transformer. So you might have designed an electrical system which works very cleanly on the utility side, but when you switch to the genset, you can have all sorts of problems. So here's some examples of some other waveforms. So this is the current distortion for a 6-pulse rectifier. This is the voltage distortion on the utility. This is what it would look like on a genset. Similarly, this is for 18-pulse. You know, with an 8% current harmonic distortion, you can have a fairly clean voltage distortion level here. But when you're on the utility, it looks quite different. So what are the impacts of nonlinear load harmonics? I think Julian talked about this a little bit more, right? So you have, apart from the 60 hertz fundamental current, you have other currents at higher frequencies. So who was paying attention to Julian? What does that result in, right? I guess the hint would be last year, right here. Yeah, you have the extra current, right, for the same kVA rating, so you're having some overheating issues. You can also have issues with negative sequence current flowing in the neutral. And if you don't size the neutral in a 4-wire system to be large enough, then you can overheat it. So again, you know, you have the voltage distortion, and you can result whenever you have control systems, you know, keeping track of the voltage waveforms as part of their operating, and they can start to have some problems. So with that, I'll talk a little bit about the UPS. So of course, many facilities rely on generator sets for supplying emergency standby power. But in some cases, you always have those equipment which are very sensitive and can't tolerate too much fluctuations in voltage and frequency. So they would not work properly on a genset directly. So we can put those on the UPS and put the UPS on the genset. But operating a UPS on a genset can lead to its own set of problems, right? And sometimes UPS manufacturers work with genset manufacturers to resolve those. Sometimes they don't. But what are some of the problems that might arise? You know, again, you have the UPS, which consists of a front-end electronics, which takes the AC power and converts it to DC, uses that to charge the battery, and then that on the other stage is converted to inverter and supplies the loads. So you have issues, again, with harmonic current. You might have problems with UPSs when stepping loads on the generator because they have a limit of how much frequency deviations or voltage deviations they can tolerate before they disconnect from the UPS, from the genset. So generally what we recommend is that, if you can and if you don't mind cycling the batteries a little bit, start the UPS loads last. But I guess if you're a data center person, you might not like that. Because otherwise, every time you have a transient event, the UPS might disconnect from the genset and reconnect, and then you have all sorts of voltage and frequency fluctuations in the system. Then if you might have issues with voltage rise, and this is quite common when you size a genset very close to the UPS rating, and you operate the UPS lightly loaded. And I'll give you some examples. And then, again, because of sometimes the tolerance for the UPS controllers, they can't handle, I guess they have a limit of acceptable slew rate, and slew rate is the rate of change of frequency. So generally, if you set the window too tight when you're running on the genset, when you have transient events and shifts in frequency, they might disconnect from the genset, or you might not be able to synchronize it to bypass. So another interesting problem is with automatic transfer switches. Generally, if you have a UPS, for example, and let's say if you have a motor, they'll have a transfer switch which connects it back to the utility when the power comes back. But what can happen is that during the transfer, let's say you have the motor, let's say you have the UPS with a large capacitor in the filter. That might provide so the motor and the UPS will disconnect. The inertia of the motor will keep turning the rotor, and the capacitor from the UPS filter will provide the reactive power and essentially turn that motor into a generator. And then there'll be some phase shift. And when it connects back to the utility, it'll be out of phase, and it'll force the motor back to the frequency and phase of the utility. So that can induce a lot of mechanical tension. So some recommendations for UPS. Currently, the GenSize tool uses some rules of thumb for oversizing. So let's say if you have depending on what type of rectifier you have, if you have a 6-pulse rectifier, it oversizes the alternator by 40% of the load rating. And if you have a 12-pulse, it's about 15%. The other thing is that isochronous governors are required because you don't want any droop in the frequency. We always say size for the UPS nameplate rating, and sometimes we get challenged on that. But I guess the idea is that you want to make sure that you keep in mind the future growth, right? You might have more load on the UPS in the future. And of course, you also have to keep in mind the battery charging requirements. So if you have those large data centers, you could have extra 25% of the kVA rating of the UPS just to charge the batteries. So if you size purely on the loads on the UPS, you might not get those factored in. So how do you deal with redundant UPS? Let's say if you have an N+1 system, do you size for the N or the +1 as well? I think if you size for the additional redundancy, you might become too lightly loaded. So I guess one thing you can do is size for N gensets and then just factor in the battery charging requirements of the additional UPS systems. So again, it's all a trade-off, right? When it comes to UPS, do you go for a larger generator to mitigate the effects of the harmonics caused by the UPS equipment? Or do you spend more money on the rectifier technology and front-end electronics so you can size a smaller genset? You can always use filtering to help with the harmonics also. I guess it's a case-by-case scenario. Another thing I want to talk to you already saw this curve earlier today, right? Hope you didn't forget it. Again, what you should avoid when you're on genset is a leading power factor condition. So what does it mean when I say that? So your load is now operating at the leading power factor. Right. So now you have the load supplying VARs back to the alternator, right? And there's a limit to how much VARs that the alternator can support. So typically, like Julian said, that there's a sweet spot right around here that the genset alternator will operate. If you go here, you have rotor overheating, and this is the instability. So typically, the PCC controllers are set to have about 20% of reverse VAR, beyond which it'll shut off with loss of field, right? Loss of field, right? Yeah. So the conditions where you might lead into your loads supplying VARs back to your alternator is for lightly loaded UPSs with input filters, or if you have power factor correction devices. So let's consider one scenario. You have a lightly loaded UPS with a filter on that's fully rated, and now you connect to the genset, and you ramp the UPS onto the genset, and all of a sudden you have a mysterious rise in voltage. So you know right away that there's an issue with the reverse VAR. The VARs are being sent back to the alternator. The voltage keeps rising. So there's two things that can happen. One is that the voltage limit will exceed what's tolerable by the UPS, and the UPS will disconnect. The voltage will go down, and the UPS will try and reconnect, and the same thing will happen again and again. The other thing that could happen is that the voltage would continue to rise, and as the voltage rises, the excitation, the AVR excitation will continue to go lower and lower and lower until you shut down the genset because of loss of field. So you want to avoid those scenarios. So if you have this situations where you have a lightly loaded UPS bypass the filters, I think there are some UPS manufacturers where this can happen automatically. If your UPS loading is less than 30, it'll just bypass the filters. And then avoid using power factor correction devices with the motors, to help improve power factor with the utility when you're running on the genset. And also helps to avoid your lagging power factor loads first. So like I mentioned before, try and start the UPSs last, because if you have those motors and high inductive loads in the beginning, they'll help to absorb the reverse VAR, so the alternator does not see it. So with that, I'll kind of jump into variable frequency drives. Again, these are becoming very common because they're used for motor control and speed and direction. And this is some typical configurations. You'll initially have some front-end electronics, which will be seen by the genset, which will convert the AC to DC, and then you'll have a second inverter stage. And you'll have some modulation techniques to control the rate, speed, and direction of the motor. So in this case, it's a simple diode bridge input. This could be an SCR. But nowadays, I think what's seen much more often is that you'll have two back-to-back voltage source inverters with PWM. And those are much cleaner when it comes to harmonics. They are very reliable and cost-effective. And I think they work very well from anywhere from half horsepower motors, very small motors, up to 500 horsepower. This kind of configuration, I guess, was used for 50 amps or less, and this was for 50 amps or more. Generally, for the front-end electronics, I think when we had a fly-in a while back, one of the consultants who was here said that the general paradigm is that if you have a horsepower, 100 horsepower or more, typically you should be using at least 18 pulse or better. Anywhere between 15 to 100 horsepower you can run on a 12 pulse rectifier, and 6 pulse with a filter or with a line reactor is typically limited to 15 horsepower or less, because they cause so many issues, especially with the source control rectifiers. So some issues with VFDs, again, we discussed the problems with harmonics. VFDs have many protective shutdowns. They're very sensitive, to frequency and voltage fluctuations. And many of the old legacy VFD equipment have a complicated restart process. So once they disconnect from the genset, it takes a long time for them to restart. I guess one of the other big issues with the variable frequency drives is regenerative power. The other thing to watch out for with drives is this regenerative power. That's the biggest concern, especially when you have elevators and cranes and things like that. So I have some slides on that. But here's to your initial question with the especially with the drives with the silicon control rectifiers. Those are really bad because they cause severe voltage notching. And this is a phenomenon which occurs during the commutation process sometimes when you have the two switches and they both turn on at the same time, so you have an instantaneous short circuit. So what that causes is that it causes the voltage to drop down to 0. So what this can cause is artificial zero crossings. And many of the motor control or drive control systems rely on the zero crossings for speed control, or if you have your SCR firing sometimes based on a self-commutating system. So they fire at a certain angle here, and once it drops to 0, it'll switch off. So that can cause some problems, and this can also impact genset controls, like I'll show you. So going back to Julian's discussion tomorrow, again the advantages of PMG excited alternators. So let me focus on shunt excited alternators and what can happen. So again, as discussed before, the power to the AVR is coming from the output. So if you have scenarios where, in this case, so let me back up a second. So this is how this is now the sensitivity of the voltage regulator, right? So this is on the genset alternator equipment. So if you have a SCR controlled excitation system, this is how it typically works. If you have a nice, clean sinusoidal voltage waveform, then what it does is that the SCRs are triggered at a certain alpha angle, and then so basically that's when they turn on, and once you cross the zero crossing, it switches off, and so this area here is proportional to the amount of power that the AVR is going to be providing for excitation. So let's say now you have a variable frequency drive or some other nonlinear load which is causing those voltage notches. What can happen? So now you have the SCR turns on, but then you have the artificial zero crossing. So the control system thinks that it's reached this point, so it shuts off early. So now your average power from the AVR is less. So then the AVR tries to overcompensate that. And then all of a sudden, you have, so initially you have the voltage drop, the AVR overcompensates, the voltage oscillates. Since the kilowatt is proportional to voltage, the kilowatt also starts to oscillate. So then you can have issues with the pulsating governor action and oscillating frequency too. So these are, that's why it's very important. I think better alternative to those kind of systems is pulse width modulated exciting systems. And I think that's that most of our gensets have PWM exciting systems, right? So rather than using the SCRs, the AVR provides power in like short pulses, and then it uses through RMS sensing to monitor the voltage waveform. So this phenomenon pretty much gets invisible. So okay, the main thing that was the issue with the regenerative load. So reverse power needs to be considered because there's a limit again of how much real power the engine can take back before you start motoring it. And I think our controllers again are set at a default setting of 10% of the genset rating. So that's something to be aware of. Actually, in our controllers, we have two settings for reverse power. One is the reverse kilowatt threshold, and then there's the reverse kilowatt time delay. And so it keeps track of the threshold. If the reverse power exceeds a threshold, then it starts an integral. And if that integral reaches the value of 1, it's just a proportional integral system. If it exceeds 1, then it'll shut down the genset for overspeed. And then the time delay basically adjusts the speed at which you reach that, it reaches that value of 1. So the only thing you have to be careful about is that the integral grows faster than it decays. So if you have an oscillating system, you might go closer to 1, go down a little bit, but eventually, over a period of time, you'll reach and exceed that threshold. So let's say if you have a load in this configuration where you have a 400 kilowatt lift, which has the possibility of 200 kilowatts in reverse power. So if you want to make sure that it's not seen by the genset, if we have a 50 kilowatt of lighting and 50 kilowatt of auxiliary load. So if we install a load bank of 100 kilowatt, then assuming that all those loads will be connected to the genset at the same time, we can prevent any of the reverse power going back to the genset. So we always recommend using load banks, especially in those cases where you have a small building where the elevator is your biggest load on the genset, because those can cause some issues. All right, so just to conclude this section, I guess before we can do some fun exercises in the big screen. That's great. Shucks. So when it comes to reactance of the alternator, I think generally subtransient reactance of 12% or less is good, but again, it all depends on the nature of the load. And then sometimes if your load is primarily nonlinear, then we say that apply the class F temporized ratings for the alternator, so that you build in a fudge factor and oversizing. And then, like I said, PMG excitation is ideal, so you isolate all your problems, that are caused. You isolate your AVR from all the problems caused by the loads. And then for UFDs, specify genset compatible equipment. So, if you have walk-in features, make sure that you can open up the acceptance for the slew rate and tolerable voltage and frequency dips, so that they can operate properly on the genset, and avoid in general any leading power factor conditions.